what do I have tried for this. So if you want to try go through the data sets, it's in Google.
Sorry, just a quick question. Are you going to share the slides after the presentation?
Yeah, I'm gonna send it to you.
Yeah, and also, can I go ahead and record this presentation, and we can put it on YouTube?
The presentation,
Yeah.
my voice, you mean?
Well, this whole thing, your screenshot. Yeah.
Okay, yeah. I can send you the presentation and the code and all, and you can do
Sure.
it.
Yeah. I mean, if you have audio, also capture any questions we had and things like that. The session, if somebody wants to look at it.
So,
Capital A and awesome sauce is one word. Studio 89. You will see that.
okay. So now these were the competitions about data. What the data is, you can just hit and show you. You can download training data, and how they want the samples to be, and also describe what the data is. It's like they have 785 columns, and each column is represented. They have like image of 28 pixels by 28, and they have 78 core. However, they have one more column with training set. This shows us what the image represents which numbers. So if I wanna show you here the data I have downloaded. So here, if we go, it's a huge data. So it's file. And also an R, I took one data to run it to say how it's run. If I want to move it and run it in R, it's got a couple of hours, and that's why I took partial. How many columns did you say that? 785. Column, I think 42,000 rows.
No, this is like if you take a 28 by 28 pixel image as data, each pixel is a number. So 28 times 28, 784. That's the number. That's one of the ways you can look at an algorithm.
They have the first column. This is the training data set. This represents the level which is like number 1 to go from 0 to 9. So these, like here, it goes up to 784, and this number representing the colors of that. So each row representing 1 pixel, 28 by 28 pixels. Okay. So that's in the one of this data is the same, but does not have this one, this column. Okay. So we'll keep it open here, and
so 0 to 255.
no, the number 0 to 9.
0 to 9. But I think from hundreds.
Those the pixels, the 0 to 55.
Okay. Yeah, this is like the intensity of the picture.
Yeah, the intensity of that. So the numbers will be like interactive, and someone transferred these to pixels and put something in a row. So you wanna, like, if I have this kind of data, can I try to predict which number we will be. That's the whole competition was about. And here just to show you how they want this. They want like let's see the image one representing. It does not have the solutions because this is a sample problem, but they need like this testing data needs to be like this, and the next column representing the labels. But this is just like a sample how they want to submit the solutions. So go back to the presentation. Yeah. So determine what this is. Okay. Next one here. I'm gonna use algorithm called K-nearest-neighborhood. Okay, I'm gonna show a little tube, just like 2 minutes. And tell you what the KNN algorithm.
Oh, okay. I don't know if it's connected to your speaker.
Sorry?
I don't know if it's connected to your speaker. We need to mute all the.
Welcome to iClassify. So what is a K-nearest neighbor algorithm? Let's take 2 example classes. Say we wanted to be able to recognize the difference between dogs and cats. How would we do this? Well, firstly, we have to identify some features that can easily distinguish them both. Well, generally speaking, they differ in sound, and cats' claws are sharper than dogs. So here we have the identified features of sound and claws. With this, we can draw a very quick graph with the axis of sound and claws. So as you can see, the cats will normally cluster around the points in the top left, and the dogs at the bottom right. However, what is a star? Is it a cat or a dog? This is how the K-nearest neighbor algorithm works. Firstly, we have a variable K. With this, you assign K a value from 1 to the total number of examples. In this case, we have 7 examples. The best value to choose for K is a low odd number, so K is equal to 3. With this value of K, we'll look at the 3 closest points on the graph from the location of the new example point. From the previous graph, I have drawn lines from the new point to the 3 closest points on the graph, because K is equal to 3. If it were 5, then there would be 5 lines. If it were 7, then there would be lines to all of their points. The next part is to assign the new point a class. The class type will be determined from the majority of the closest points. In this case, the star is a cat. Since majority of the points are closest to the cat's characteristics than the dog's characteristics. Simply put, assign K a value, preferably a small odd number. Find the closest number of K points and assign the new point from the majority of classes.
Okay, so there's like many of those YouTube. You can just go through them and get more. So I also include here pictures. It show you like I want to find out what star is. This is a class A or class B. I want to classify these things. So K nearest neighbor, which is KNN. You have to choose in the beginning what's K, which value. You can run multiple of those Ks, like just in any simple language. You can write small loop to choose K from like 3 to 20, See, like for example here, if I want to classify the star and I choose K to be 3, so it's gonna be class B. However, if I want to take K as a 6, you will find that it's more in class A. So you want to run a multiple data, 1,000 of data, different K, and in the end you find more the accuracy to get this one more higher, like 90%, 85%. That's more to classify this to this.
And also more data points in your training set, more accurate.
Accuracy will have. Okay. So next things I'm gonna talk about R. I'm not sure who is not familiar with R. All of you know R?
I won't go that far. I know what it is.
Okay. So R is the language and environmental statistical computing and graphics. It just do a lot of statistical algorithms. It has tons of libraries. It's not like old style language like Java, C++, things. You can just call the library, and this library has a ton of things to do for you. Just in one line, you can call it does stuff for you. So like the KNN, it's already built up library in R. You just call that and give them the test and training data, and they will run the algorithm for you, and that's all. So you just write a couple of lines before and a couple of lines after how you want to design your program and run it. So from where you can download R, I just include, click here. It shows you the option of run it for Linux, Windows, and any operating system. So you just download it. When I have it already here in my computer. So when it is open, it shows like this. Like for example, 5 plus 2 hit. It will give you like another language. So this is R, but there is another more powerful studio for R, which is also you can download it, and it's a little bit different. I usually use R Studio. It's more powerful. So also I include the link for all for us if you want to download it. You usually wanna go with the R Studio personal license. It's for free, and you download it, and can show you here the difference between R and R Studio. It's you can put your code here and run it here, and it show you which data, and here you can include which data you have. It show here. I'm gonna show you more of those R Studio when I run the R code and see how it's powerful than just regular R. Okay, what's next there? So, oops. Okay, so done here, like I'm gonna show you now what's R and how did I write the R code and try to go line by line. I have done these things. So okay, so for my code, I need to run two libraries. Usually, if you want to run any library in R, you just call library, and this is the KNN and class to do some of those code I needed. So how do you call those? So you read the file, and where do I have it? And just highlight it, and you click Control Enter. And now I'm trying to load the data to my file here. Which is usually included here. I'm gonna show you a little trick. I like it in R, but when it is finished. So usually I put my data and I create a project in R. Just go in the top here and say create a project, new project, and give him the name. And put the icon for the project and your data in one file or one folder. And when you open the project for all of your data is going to show here. So it's more easy to the R to load your stuff to the R. And here the R is going to keep running, and it show here the stop sign. So that means it's still running until this sign is disappear. I can go and start the second line in my code. So now it's finished loading it to the program, and it show me here. How do you get rid of this? Okay. So now when I read this file to my code, it comes over here. You can see that the training data is 785 column. Over the testing data is less by 1 compared to the train, which is the first column, which is the label is not there. That's what we're trying to do. And now if you click, for example, add these things, or write here in your code a view, it will show you the data, but it's not gonna show you everything. It's gonna show you just a part of that. Like for example here, this data is gonna show you like until probably 100 column. Oh, so it's not gonna show, but you can specify by your code, like if you from line this to line this, or from column to this column. So here, just like show me 100, but it's there, but because the screen or the monitor is very limited, so it does not show everything. So we don't need this one, and it's the same thing. So now, also I can click here to view it, or I just go and type train, because by using this and R, I put this under this name. Like this is the variable name. So by type it again, or click it, add it, or write a view, you do the same things just to show me the data set. Now, also in RN, if I want to find the dimension of this things, like if I just try DIM, the training, or DIM, the testing, it shows me that it does have 42,000 rows and 785 columns. Okay, so now I wrote a couple of lines to show how these data will be plotted. We transfer these pixels to plotting. So each row to a picture. Okay. So that's how I did this code. So in the training, I took all the data sets minus 1. In R, I don't know about other language, but in R, yeah, but in R, they start the matrix or from 1. When I subtract from 1, that will include everything in the column except the first column. So I subtract the label, which is I don't need it when I draw. So I subtract it, and I use another function that's do call. Like I'm calling some argument and put him in one line. So just calling. So I want to rebind those together and apply and list them. So those data will become unlist. So I want to unlist them and put them again in one matrix.
Each row is a picture, is it? Yeah.
28 by 28 pixels. Okay. So if I run this code, watch this, the right bottom, just highlight, control, enter, show you the handwriting, how it was. So now if I want to change here, I want to go rows 560. So you can do the loop to draw all of them, but I don't want to draw all of them. I want to just show a couple of examples. I'm just going row 565. Highlight it again and click enter. It show you like this is might be number 5. Another examples like go higher number, highlight. Run the code again. I don't know, might be 9. That's handwriting. So that's what we want to find out to try to classify if this is 9, 8. Okay, so because the data, anyone has any questions so far? I don't know if it's gonna work in. Sorry?
Bar, the manual bar. The view where you
Oh. This is better? Okay. Try one more. Okay. So now, because the data it's very big, I cannot take all of this data and start running it. So I took part of that or partial of this data. So where did I?
Where did you apply your algorithm?
I haven't applied. This is just like trying to load the data and view the data. This is just the data. I haven't run any algorithm. Okay. So here, just I said this is a plotting. I put these to show you what's the difference between unlisted and listed. I'd include it here. Now I'm trying right now. Column number 1 in the training is the label. So I'm trying to take that column and call it in different name, labels, and take only the 1,000 rows. I don't want to run more 1,000. It's a huge, it takes maybe 10 hours to run it. So just 1,000 to run it in 1 minute or 2 minutes. I have to take this data and transfer him to what? To a factors. To encode those and change him from is a vector to transfer them to classify them and use them in the algorithm. This is how it's the KNN and how it goes on. You have to specify this as the factor. So put this column, give him a name, and keep the variable aside. Now I took the training data from 1 to 1,000 and I -1, so I only have from 1 to 1,000. And also I take the data from 1 to 100, the testing data. I don't want to take all the testing data. I'm just taking like 1,000 from there and 100 from there and try to run the code. Just here, generally, I'm trying to show you how you run the code. But if you want to run all the code, you don't need this. You just take everything. Okay, I hope this is clear for all of us. So now, how do I run the code? As I said in the beginning, just call the library in the top, here. And then that's exactly one line to run the algorithm in R. That's the powerful about R. So what you need, I want to store the new data in label. So I call the function KNN open the training, the training data, which is just 1,000 rows. Yeah, that's R. It's library in R. And then I took the testing data, which is just 100 row, and I take the labels, which is just 100 first column data, and I choose K to be 10. I can't choose it anything. It's just, you can also probably write loop here and KI and run multiple K. This is just an example to show you.
Which AK work the proper K?
You have to do a lot of Ks to find out which one is the best.
I'm going to fill the customer will label 0, 1, 2 to 9. That's why this.
K is the number of nearest neighbors. K.
Yes.
So this is not the number of classes you have. That is different. Your K would be higher here.
Okay, here, if you look at the pictures here, K, it's how many closest neighborhood to that star I want to classify. So it's not the number. It's like, I'm choosing N to K with these, so I'm going to find the closest 3 neighborhood to the star, which is the 2 neighborhood and 1 neighborhood.
By the way, in this picture you have 2 classes, right? And we are talking about classification of N. So this is just a one depiction of 2 class classification. But your K could be 3 or 5 or 6, whatever.
So it's just K is just to find what's the closest neighborhood. To choose, you can choose it.
But in your case, how many classes you say?
Only 10 from 0 to 9.
So it's only numbers.
Yes. Yeah, no letters, just like 0 to 9. I have the training of 1 pixel. I don't know which number is represented. So in the training section, I'm gonna use that one, which is already classified, to train my algorithms to find what's these data, which is we don't know. So this is the algorithm. So I'm gonna just go run these before I do my algorithm, and watch here. All of this is gonna show the value and what each value it does. So now if I wanna run my algorithm, now it's finished. So now
So what is the code is usually doing here is that find the distance, each of the vectors, and find the distance between the vectors.
yes, that's the whole thing.
Yeah, but I think it just lays out the space.
Yes.
Where it lays out the training set in a space. In this case, 784 space. Then if you want to give a test item, we place that in the space, calculate the nearest neighbors, say which one.
Yes.
What the majority.
Calculating the nearest neighbor by just measuring the distance.
Yes.
Or just draw in a circle and include those with the area. Anyone is like this. K, it's more a statistical algorithm. It shows a lot of math. There is a 3 method to measure the distance. Usually it's statistical. So I didn't include any mathematical. Some people are far away from math, so I get confused. So it's just a picture. So.
But might be close to someone.
Sorry?
Might be close to someone.
I leave it for you guys to, if you write just K and an algorithm in Google, tons of like, tons of reference you can read.
Yeah.
Well, we could, if there is enough interest, we can probably do that in the next presentation.
Yeah. But people get sick of math. No, I like math.
Yeah, I mean, you get 1 star in the 5.
Yeah. So when I run the algorithms, I store them in a label, and now I want to just put them in an Excel sheet because they ask us to include an Excel sheet. So I just add the label and go okay, and I put this label over there. So if I run this one, a new folder here, Excel sheet will just save. You can pull it up from here, or you just go to the original file where you start save all your file. I just include, and it show you those, the training, which is we choose 100. Show you which one is representing. Okay? Maybe we stop with 9, I think. Yeah. I think they include this. Is starting from 1, yeah. And I think it's a little bit, you can, yeah, there's something here wrong. It can be fixed. So, then I want to show you how to find the accuracies of what we have. How do we do that? So I took the training, which is 1,000, and I took the testing data and I put them together. So here what I just from the new, I have the label, and I have the test one, which is about 100. See, just add a column to the first. So I just put the label with the test, and I show you the new column new test. So if I run those together and I go to the new test, it put me the numbers here. See, this one does not have the 10. Does not. So it's just like probably when I transfer it to Excel, something happened wrong. So here it's just 100, and I add the new column to it. And then what I do, I took the 1,000 training rows with 100 test rows, and I put them together. Like I put first the training, and then I do put them the test together. So let's just run this so we don't forget. So then what I do, I shuffle those rows up and down. So I use usually what they call run F, okay, and regard a new data set. So it takes whatever, how many values in these things, and you create shuffle algorithm between this number and shuffle them together, just switching the rows together. It does not switch like there is a column in the row and up. Shuffle one row up and down. Okay. Sorry? Yeah, that's I want to find the accuracy. Okay. So does shuffle here, and this is again I want to choose different data set and training set. Sorry? I'm not familiar too much with Python.
You could do that. I mean, all that we need is a map that goes random. You could create your own.
I think some post function already built them because this is built on an R. So after I shuffle them, what I do, instead of choosing 1,000 from the new, which is 1,100, I said like I'm gonna choose 1,900 for the training, which is like from 1 to 899 and minus the first column, and I then for the training, okay, I choose from 900 to 1,000 minus the 1. So I'm just choosing those without the labels. And then I took the new list, which is from the training, okay, and I took only the first column, okay? And the second one, I just took the training from the testing, I took the label one. Not sure if this is confusing or clear. After I shuffle those, they will become 1,100 rows. Okay? And then I choose 900 rows from the training and 200 rows for the testing. And I remove the label column, which is the first one, and I store them in different variables. This is what I did. So what I did this again, I'm gonna run the code again, the same algorithm again. So let's just run this again. Okay, and then I'm gonna run the algorithm again.
What is the criteria used to make a decision that these 2 points are near stable, so at the same class?
Distance.
Okay, so what is the?
You want to find what's in the KNN algorithm inside R.
What's the length or the radius of that circle? Because if you change it, you decrease it in margin.
The circle is a virtual thing. It's not.
I know.
It's just like I said, I want to find the closest tree. So I measure all the distance around that specific one. And I choose the closest tree. So the circle is virtual thing.
I know it's virtual, but finally you have to say this. I mean, when you do the algorithm, there's an next step. It is less than.
Are you talking about what's the distance?
Tolerance, the distance.
Okay, well, you could start with just the interior distance.
So, imagine I'm here. Okay.
Yes, I know, but
I want to classify myself. Just listen to me. I want to classify myself if I am belong to this group.
Yes.
I said I'm gonna choose K to be 5. So I'm gonna measure my distance. All of you. Yes. Who's the closest guy for me from the ocean?
But it's really not distance, is it? It's weight. If I'm 11 and you're 5, you're measuring the difference between 5 and 11, aren't you? You're not measuring, you're not saying I'm 8 feet from you or 8 millimeters from you or 8 inches from you. You're saying I'm 11, you're 5, therefore the difference is 6.
Yes, it's not that distance.
Distance always like relative.
No.
The number of nearby neighbors.
See, we are not talking about that distance because we don't know whether it's 5 we are looking at or 11 we are looking at or 9 we are looking at, right?
Yeah.
Because you only know the pixels. So you only know the vector there. It's actually, think of that as a 784 dimensional vector in Euclidean space and that many dimensions and look at the distance. As simple as that. And that works.
So it's not completely wrong, but you mentioned it in space.
If you're talking about one dimension, yes.
Yeah, that's what I said. Yes.
But here we don't deal with one dimension. It can be infinity dimension. That's why
You test
Yeah,
has
infinite dimension.
So could be, yes. That's why I said like when it's the algorithm.
Well, if you are looking at the distance in 784 dimensional space, yes, right? So you can realize that.
So that's why it's very lovely with the math. You know, it's
And also which candidates to try, it doesn't have that distances to everything in the stack. But it has a way that it makes the structure, it actually makes a data structure on KDP. Where log of this state and in that you can easily get to the nearest neighbor. That's something you may want to look at.
See, guys, if you have a lot of math you want to deal with. So this is the 3 method to find the distance. Lovely math. That's like the way I would define the distance between those. There is 3. Okay.
Because the distance is just any t.
Yeah. So it's, if you wanna just talk about math, it's different story here. So it's just try to show codes and how stuff is.
Das can require the data to be normalized first. That's
Sorry?
normalize the data first.
Yeah, there's a preparation process that goes on, and this data is already prepared. So you have the digit fitting nicely in a 28 by 28 pixel image, and that is done. If you don't do that, there's no way you can get the. Yeah, it is a prepared data set.
Sorry, another question, just a little bit off track. So we shuffle data set. These are unstructured data. What if we have structured data set? How do you do this kind of shuffle?
Unstructured data?
Why is this unstructured? It is structured. You have sharding for regular columns.
So what it means that each row has no dependency or relationship with the next one.
Yes.
That's what I mean. Let's say you have huge data. How do you reshuffle this? They're dependency for that. They want to have dependency on the minus one.
That's a different. Here we're dealing with the structured data. Every row is totally dependent on the other rows. That's different ways. Mathematical thing.
I'm serious. How do you prevent the
I think that's a different problem.
Yeah, I got it.
Let's not talk about
It's off check.
Yeah.
But you think dependency on the shuffle random? No, I don't think so.
You cannot.
You not shuffle random?
Yeah, shuffle, but just dependent. Structured data. They're not dependent on each other. Each row is totally dependent.
Okay.
They will make them on the shop. Just be able to test the performance ready when you are given the time and experience data, you will normally move data together. It's like maybe you come up with one model to be price of stocks. You've having had the data for maybe 2000 and then CAC. Maybe you have your models based on 2014 and then 2015. You want to test on the 2000 and the CAC. You are testing on the tongue. So you can your hand just short them together. You can mix the data of 2016 with the previous you get from your test. The not is one that have corrections, documents about this day, the reflection that I can say this data, you have to use them together. Test by maybe window of time, maybe this one, this one, and this year,
The one way, I think another way is possible is like when studying Windows.
Yes, yes.
My student is a 1 year data. I study only forward, move forward. That use it and you can wherever I could find that's kind of E, for example. Yeah. But still, it kind of it's not either way to put that on board. You have one way to that's possible.
Yeah,
You have to change your data. Yeah. One data set is much less basically.
Yeah.
Yeah, it's okay. We're learning here. So after I do that, then I run the algorithm again, and then I put the, you know, the false true matrix. Yeah, and I do the accuracy here by try to compare those together and see what's the accuracy of the old, the testing, which is I save him here, this one, with the new one I just run. Okay, so if I run these two, the last two lines, it show me here the accuracy of my algorithm with k equal 10, so you can choose any k. It's 85% accuracy, my algorithm. Okay, and this is the matrix here. Okay, it shows you from 0 to 9 and from 0 to 9. It shows like there is 0 and I find 18 0 and like 0, it's 100% accuracy. There is nothing else here. So if I go to the 1, also 21, which is can be 100%. Now if you jump in 2 with 2 to find if they are the same, is it 24? However, there is almost 4 of those. It's supposed to be 2, but my algorithm, it shows is confusing 4, and that's how you read the matrix. Just to explain how this matrix is. I think they call it false true matrix. True. Yeah, it shows you like here number 9. It's supposed to be 18, but there is confusion between 7 and 9, 5.
So just a quick question. When you do the shuffle, only from this matrix, right? The 10 by 10 matrix, only do the shuffle reading this matrix, right? Not the big matrix.
Yeah. Okay, this is. I think this is might be confusing for some of you. When I ran the first code, I took 1,000 and I took 100 from the original. Yeah, from the big data. And then I run my code and I find the answer for the distance. Okay, and I took those together, 1,100 and 221. Okay, shuffle them, and then I divide them 900 to 200.
When you say 1,000, you took 1,000 rows and then 100 rows, right?
From the testing and training.
And then what you ended up with a 900 rows and 200 rows, but they were shuffled.
Yes,
right?
Yes, after I shuffle.
After you shuffled.
But the remaining 100 was from test.
Yeah, from the test I already find the letters. 1,100, shuffle them, then I divide them to 900 and 200.
Well, one of the methods people use is this automatic training set, where you know all the mappings of the right answers, right? Some people set aside about 20–30% of data for validation. So you run the algorithm on the 70% of data, and you test how your algorithm did on the remaining 30%, and then run it on. That's one other.
Yeah, I'll talk about the doing it, but I might make it more.
Okay.
So you can take in the beginning, you see your code is taking the training, dividing 75%, 25%. Okay? And then run the algorithm to the 25%, which is the distant data. And the distant data already have the classified Then you can compare your algorithm with the original classification with the new algorithm as classification, and you can find the accuracy. But I try to do it together, I might confuse a little bit, but that's how you feel like we do the accuracy.
So the training and test data gets broken up as training, validation, and test. So validation comes out of the training. So that's one way of knowing beforehand how your algorithm is doing.
If you are testing the model on the data that you use to train, it is like you might not get the true performance. That makes sense. You say you are testing the model using the data that are used for the training.
I use only 100 from the distant data, not from
Can I set this up in your?
Yeah, sure.
If you're you're having a mix the training data with the test data, then shuffle it.
Yes.
And then run the model again.
Okay, so okay, so I was on mute because there was a feedback. Okay, so let me share my screen. Okay, so yeah. No reason. I mean, it's just that Google Cloud is handy.
That's the same thing, really. You know, AWS. I mean, I don't think many people are using Google Cloud yet.
Sorry?
Yeah, I was just curious.
Yeah, but it's the same thing.
It's the same thing. I mean, I don't know. I mean, I happen to be familiar with Google Cloud, more on Google Cloud at this time than on AWS. In fact, I could do the same thing on AWS. It's just that.
Yeah, you're still going to set up a server. You're still going to set up Apache. You're still going to set up.
What I'm going to do is, yeah, that's going to take time. What I'm going to do is, I'm going to click a few buttons, get the whole thing started off on the cloud. You know, they have a service which brings up the whole thing. Dataproc. Yeah. Okay, so let's get started. So I prefer PDF than PowerPoints because, you know, with PowerPoints, you know, the cursor disappears. You know, I won't know what I'm pointing at.
By the way, in R you can make PowerPoint presentation.
Yeah.
Very powerful.
Sorry?
In R you can do PowerPoint.
Oh, yeah.
Very powerful. They do it like as a PDF file.
Oh, okay.
Very powerful.
Okay. So anyway, I mean, initially I thought I'll go first. I gave the introduction. So the first two slides are, you know, just introduction to what we do here. So the next meetup is on November 13th. I guess that's a Sunday.
My birthday.
Oh, okay.
My birthday.
Okay. So that's going to be here. So the agenda today is we'll just talk about Yarn, just one slide. And we will talk about Spark computing model. So just an introduction to what Spark is, what it does. We'll not focus a lot on how it gets installed. That's going to be a whole new thing. We just bring up a Spark cluster and just give an overview of how it works, and then what we could do with that. I just have a couple of examples. And if we have time, we will just, the idea is to start an activity in machine learning. So scikit-learn is one of the libraries that you could use. Other than, there are many libraries. In the Python ecosystem, scikit-learn is one of the libraries. So I'll just show you, a simple example of how one could use scikit-learn. And that would be, the example here is just a curve fitting example, which you'll all be familiar with. So this is just to get you started. And then we'll just talk about, if you have like 10 or 15 minutes time, what we could do in the next sessions to actually continue this activity. Okay. Now, Yarn is a cluster computing. You can say it's an operating system on cluster in the Hadoop ecosystem. In the last meetup, Murli gave a presentation covering Yarn and a lot of other things. So basically, yeah, Murli is right here. Yarn basically is this. It will give you an interface to a cluster as though you're working on just one operating system. Even though you have in a cluster you may have multiple nodes and each one is an OS by itself, right? So the way Yarn works is Hadoop basically has a master-slave architecture. In Yarn, well, Hadoop has majorly, at a high level, it has two components. You have an underlying file system, and then you have a resource management system called Yarn. So this is how it works. So if you have to run a job, you have to ask for resources, and this is resource manager is the stuff you go to ask for resources on the cluster, and so that's the protocol.
You probably have like multiple yarns running, or just in case of resource manager.
Resource manager is one. You will usually have a secondary resource manager. You'll have a failback server for a master node. So that's what it is. So if both of them fail, of course, your cluster fails. You have to do something to bring it up. So, but most
file system is Hadoop.
Hadoop, yeah. So well, Yarn works on a Hadoop system. So the way it works is if a client has to start a job, in this case, we have two clients starting two jobs, and they both go to the resource manager, ask for resources, and the resource manager does not worry about the, well, if a job runs on multiple clusters, if one of the nodes fail, and if that part of the work fails, resource manager has nothing to do with that, doesn't worry about that. So what it does is it purely focuses on what a client needs, and it hands over the resource to the client if you on a cluster, if that much of resource is available. The resources we talk about here are CPUs basically, and then memory. So these are the prime resources. Now, so what it does is it finds a place where it can start what's known as an app master. App master is the main driver for any job. And it's the app master that takes care of tracking individual segments of the jobs that run on different nodes and things like that. If a node fails, app master comes back to the resource manager and says, I want more resource, give me something for my job. So that's how it works. So at a job level, app master takes over once it's instantiated. So this is how it works. So in this case, you're looking at 3 nodes, 2 app masters, 1 purple and 1 whatever that color is. And then each app master will instantiate containers to run the jobs based on what the job needs. If the job is a small one, it probably needs just one container. If it is bigger, you need more containers. So this is the Yarn model. And we're going to look at Spark running on Yarn. In Yarn, you have things like the resource manager, and that comprises of basically a scheduler and an application manager. And there are scheduling policies, how the resources have to be distributed among the clients and things like that. And these are the two resource scheduling policies. Fair scheduling, it's basically equal share of resources given to applications. And capacity scheduling is for every application there's a capacity guarantee that's given. And so that's what it is. And these capacities can change according to priorities of the applications. Now we are primarily interested in Spark in today's presentation. So, well, you could actually draw a parallel between Yarn and this. So in the Yarn setup, you'll basically have a driver program for Spark and a cluster manager, which actually is included. It's a part of the driver program, but not a separate JVM instance or an executable. And when the job runs, it spawns executors on different nodes, and the executors will handle a memory cache, and all the processing happens in memory. And the data that it needs to work on gets broken into a number of partitions. On every node, you may have a sizable number of partitions, and so executors will run on one partition after another, and each one of them is a task. And if you have more cores in a machine, the executor can go on multi-threaded. They can go parallelly on each partition. So that's the model. Now, Spark itself can run not just on Yarn, but it can work with Apache Mesos. That's another operating system, a cluster operating system. And it can just go standalone as well. And in Spark, the languages that are supported are Scala, Python, Java, and R. Scala is a JVM-based language. So when you write code in Scala, what you get is bytecode, which is actually run on JVM. So, and it's Java compatible also. So you can write modules in Java and then use them in your Scala code. And Python also, even though you have a Python API for Spark, so you'll write your program in Python and submit that to Spark. But Spark internally runs the same engine as run by Scala code, for example. So it's the same engine, and Spark is implemented in Scala mostly. In the Spark ecosystem, you have Spark Core API, and these are the languages supported. And you can also run Spark SQL. This is a separate API for treating your data as data frames on which you can run SQL, and you can think of that as a table. You can add columns based on your own definitions of how columns need to be processed and things like that. And you can filter stuff out using a where clause like in SQL. So that's what this supports. You also have streaming. So if you have streaming data, you can stream your data into a Spark cluster. And it supports two kinds of streaming. Streaming based on size of the stream chunks, or it can also go on time window. So it can take the data coming in the stream between two instances of time. Well, it can break that into frequencies, and then for each time instant window, it can start run a process and then produce some results. And there's a machine learning library called MLlib, and then graph libraries. Okay, so the Spark computing model consists of this. The main abstraction here is called RDD. RDD stands for Resilient Distributed Data Sets. And pair RDDs are, like RDDs where you are talking about a key value pair in each element. So what an RDD is just, you can think of that as an array of data where pieces of that array are on different nodes. So that's if you can work on a large set of data given by, let us say, a CSV file, you can have each line as an element of the RDD, and you can basically take the whole, you can run a method on the RDD. Even though the pieces of this RDD is on different nodes, one method just does the same thing on all the pieces at once. RDD is resilient distributed data set. So that's the basic data structure in Spark. So well, think of that as an array, just a list of objects that you can store. And the objects, pieces of that will be on different nodes when you process. Sorry?
It's multi-dimensional.
No, it's one-dimensional.
Oh,
it's one-dimensional.
It's like a column.
It's like a list or just an array, one-dimensional array. Yeah. Well, if you put a complex object there, you can have a structure within that. But then you have to interpret that structure when you process it. And on RDDs, once you get an RDD, let's say take a large file and bring that onto the memory as an RDD. It means you have the whole data in the file sitting on your cluster in memory. And you can, what are the operations you can do on that? What is the kind of processing you can do? That's the question, right? Now, RDD supports two kinds of operations. One is called transformations, the other actions. So transformations give you an RDD back. Like if you apply a transformation and an RDD, you get an RDD back. Your RDD could be, take this RDD comprised of all the CSV files and break that into key value pairs. So you can make that into a RDD with just key value pairs. That's one thing you can do. The other thing you can do is actions. One action could be, if you have a key value pairs of key and a number, one of the things you can do is bring me the sum of all numbers to the driver program. That's a example of an action. And in some cases, you may have to broadcast some variables that are very frequently used explicitly to all the nodes, so that whenever you make an operation or you call a function on an RDD, if the variables are needed locally, you just send them out at once and then use them locally. You could do that. So sorry? Yeah, all of these are in cache, but then some variables from the driver, you can just make it go sit there. Let us say you're working on some lookup data that's needed for the processing. So instead of sending it every time with your function that you're going to call, you could just send them all at once and then say, you can call the function and then say, use the variable from the broadcast. That's something you can do. so that you will reduce network traffic. So that's the idea. Well, accumulators is something, again, accumulators is, if you have to have one variable that represents the state of an RDD. So let us say you are talking about how many or some counter of some kind, right? Let's say you're looking at some kind of data within your RDD, and whenever you find it, just flag something and then update the counter by 1 or increment it by 1. If that's something you have, if you have all the processes doing it, if the counters are local, what happens is each will have its own counter, and you will not know how to get that back, right? So accumulator is something where there's only one instance of that variable throughout the cluster, and you basically have that one instance updated. So you need this kind of framework in order to do your algorithms.
With regard to broadcasting, we consider latency and things like that.
Yes, I mean, if your data is sizable enough that it's very expensive to package that data out on every function call, then that's a good candidate for broadcast. Broadcast it once so that you don't have to send it every time a call is made on the RDD, right? So I mean, you can think of examples, a lot of them, with that kind of setup. If the data is very small, you can just make it go along with the function, right? Every function call just gets sent out from the driver. And while you send it out, if there's a chunk of data that's repeated over different calls, and if that chunk is sizable, and if that helps, if you just send it once instead of sending it multiple times, you will free your network. So that's the idea.
Can you give an example?
I can think of things like, let us say you're calculating, let's say the prices of instruments based on some market data, and the market data, let's say, is 10 MB, 10 megabytes, right? And so you want to do different kinds of pricings, or you're running multiple scenarios of that. So scenario 1, you do the pricing on the whole RDD. Scenario 2, you're doing it again. Scenario 3. So every time you don't want to send this much of data over the network to all the nodes. So just send it once and say it's the same data, right? So in the scenario 2, use the same market data, right? So that's something, well, so that's why you need that. One other,
I'm sending this data to worker nodes.
to worker nodes. Nodes, yes.
But then those worker nodes might not need the entire data set. For example, if they're working on,
If they don't need the entire data set, you don't have to. But there are many cases you may have to, right?
are you explicitly saying that, hey, send this 10 MB of data to all the nodes versus node 2 and 5?
No, you don't care about
You don't care. I mean, memory is cheap, but then if you increase your traffic too much, your network gets clogged, right? So I mean, you can do that kind of fine tuning, but do you want to? That's the question, right? If it cuts down on your development time, you just say send it out and then let them use the data they want.
The reason why I'm thinking around those lines is because worker node, let's say 2, is only supposed to have 2 megabytes of the 10 megabytes. How does it decide that to broadcast only 2 megabytes and not the entire data set? How is that done?
Broadcast it goes to all.
But is that the size of your RDD? Is that how you've reference your RDD. In other words, if you said it's this RDD is made up of this part of the Excel file, and then you've asked Yarn to go store it, and you have some kind of pointer to the RDD.
Well, you have a high level pointer to an RDD. You will not be able to go look at. You may actually get to some certain partitions as well, like there are those, but then for most cases, you don't want to get to that level of programming, right? Like your program gets more complex. Like you can reference partition numbers as well to do that. But then, do you want to do that is the question. If you have a use case, you probably will have to do that. Okay. So partitions basically are chunks of RDD that an executor task works on. So if you look at, if you actually recall, an executor can run tasks, and usually the number of tasks that this can run is same as the number of cores you would have allocated for each executor. This is configurable. You can configure your executors to actually use 2 cores on each node or 5 cores on each node. You know, this is something that you can configure. So if you have a 24 core CPU on each of the nodes, and if you want your process to use only 4 cores on each node, each executor can spawn 4 tasks at once. They can run on 4 different partitions within your RDD at once. So your RDD can have like 20 partitions on each node, and 4 of them is taken up for processing at each time. So that's how this goes. So sometimes, you know, while processing, let us say you start with an RDD, and then you apply some transformation that filters out some data, and you have very less data to work with. It may make sense to repartition your RDD so that you have smaller chunks, you have less number of partitions, and that helps. If that helps your processing, you know, this is something that you do. You repartition and then work on your RDD. Shuffle. Oh yeah, shuffle basically is this. Let's say you have an RDD of key value pairs, right? And you want to run an action that says group all the keys in such a way that keys of the same type or same value come together. I mean, the same key comes together, right? So this is the usual group by action, right? Like let us say you have key 1, K1 value 1, K2 value 2, K3 value 3, and then you have K1 value 5. You have 2 of keys K1s, and you want them together. So if you want them juxtaposed, you would just want to run an RDD operation called group by, and that may need shuffling data between the nodes. Like, yeah, you may have for a particular value, for a particular key K1, you may have key value pairs sitting on different nodes. That's possible in an RDD, right? And if you're bringing together, data has to be moved from one node to another.
And that does this one create a new RDD?
Sorry? Yeah, create a new RDD. You're applying a transformation. The transformation is, give me a new RDD where the elements of this are grouped by key. So, and RDD persistence is while you run your job, if a particular RDD is needed at different places, you don't want this RDD to just be like when it brings the data and when the next RDD transforms this goes out of memory. That's the default. Now, if that is needed at different places, it makes sense to actually make it persist in cache. That means through the entire life of the program. So that is when you use rdd.persist, which will allow you to just keep it there so that it doesn't have to go back to disk to get the data. And stages, they correspond to this. Spark has something called lazy evaluation. So when a code piece runs, it just forms a DAG. A DAG is directed acyclic group. Now, directed acyclic graph. What it does is it just says how to get the data, and it may not actually fetch the data until you do some action on it that needs it to go get it. So it just stores that information, and only when you are asking for an action, all the previous jobs get triggered, so that this whole thing can go run once and bring that. So that leads to efficiencies, and that's called lazy evaluation. Until you want something to be done, you actually postpone acting on it. So that's the idea. Now, because of that, the whole job gets broken into stages. So each stage is when an action is performed and a stage completes, and then that whole thing gets acted on at once. So those are the stages. We will see a few of these concepts in our examples. Okay, so let's actually, I think we have about half an hour. Okay. I will try to run this in two different ways. One way is to actually run it as a REPL, like how Mohammed ran. REPL is, read, evaluate, process loop. So what it means is, you get a prompt and you can run code line after line, and it's more interactive. That's one way. Another way is you can put all of your code in a file and then run it at once. So,
by the way, have you paid anything?
Well, actually, one second. I don't know why it's asking again. Well, Google, when you sign up, they give you $300 free. So,
60 days, right?
and 60 days, yeah. I think you can make it last 60 days easily, depending on how you run it. After you're done, just shut down your instances. You'll be charged $1 or $2, So that's the Google Cloud platform, and you see, I use it for 3 or 4 days, and I'm charged less than $6. So, yeah.
So it's like sign up my credit card. Does it like stop?
Yes, you can say you have to explicitly say convert me to a billing client.
Oh, okay.
Yeah. Otherwise, it will not charge you. Yeah. This is safe. So you have a lot of things you can do on the cloud, and we'll not look at many of those. So what we are interested in today is just this Dataprop. Dataprop is a service that gives you a Hadoop cluster on Google Cloud. So I'll. Oh, okay. I think it's control. Is that better?
Yes.
Okay. So you can give the name of your cluster as anything, and zone, US East. Okay, so Hadoop is a master and slave nodes architecture, right? So I'll choose, for our purpose, I'll choose a machine that's just 2 CPU, 7.5 GB RAM for my master node. I don't need 500 gigabyte hard drive, I just need 20.
This needs to match your.
No, this is what you're ordering on the cloud. So I'm just ordering a cluster with one master node with this configuration, 2 CPUs, 7.5 gig, and worker nodes. Minimum you need to order is 2 worker nodes. I'm ordering the same configuration, 2 CPUs, 7.5 gig, and you have to specify how much hard disk you need. I'll probably order 20 GB hard drive. And there are different kinds of hard drives you can order, so I'll just order the default, which is the cheapest. And that's all I do to create a cluster.
The concept of non-peak hours versus peak hours.
There is something called preemptible worker nodes. So if the cluster is busy, they'll put your jobs on a lesser priority on the network, and so that way you'll save some money.
So if you change the fee, that means they put your like processing to a high priority.
Yeah. You can increase your priority as well. You can
use the free account for 6 years.
60 days.
Oh, 60.
6 years is a lot.
That was the opposite.
Yeah, you could do that. Yeah. But then people would want to do something beyond just learning, right? They would want to just go have some permanent setup. So if you're just learning, I think they're okay with you changing accounts. Yeah.
Amazon gives you 12 months, doesn't it? AWS.
Oh, that gives you 12 months only on a micro instance of a VM. But with micro, it's difficult to run anything on it. I've tried. But you need to order something bigger for a Hadoop process to run. Okay, so the cluster is up and running. So I'll go log into one of the VMs. Okay. So that's the master. Cluster 1M is the master. So I'll just go SSH into that. And I'll open one more terminal. Okay, sorry? You could generate one, just like in Amazon AWS. You could generate a key, and you could use that key from your putty, from your whatever you can. But this is easy. You don't need anything. it gives you a browser, and in that it gives you a Linux shell. So okay. I don't need all the 3 windows, but I'll just instantiate it just in case.
You have like full access. Full access.
Yeah, you can sudo on this. Yeah. Not the, they won't give you root passwords, but your user will be given sudo. Yeah. So if I just, it's all loaded with Spark. So Spark and a few other things, come with default on Dataproc. So I'm just starting a PySpark shell, which is a Python shell that can run your Spark commands.
Is there a reason why you're using PySpark instead of Scala?
I could use Scala as well, but it's good to change from one to other at times, and then get a feel for one or the other, right? So well, on the earlier instances I've used Scala as well. So you could Java is this I don't know how to increase the fonts here. Control plus plus. Okay. No, I don't know. Let me see if I can do something here. Text size. Oh, okay. Is that better? Yeah. Okay. So that's the code I want to run. I don't know. Let me see if I can increase the font of this. Okay, I think I can. Is that visible? Not really. I mean, after this session, I'll put this on GitHub and I'll share the link. Okay? So you'll have access to this code as well.
There's a magnify beside the reader icon.
You mean magnify beside what?
Yes, this one.
That's print preview.
Oh.
View. Full screen. I don't know.
No, I can figure it out. I was talking to you.
Okay, so if I'm using so before I start, I'll just show you what's the data I have. Well, that's a CSV file. It looked like that, but let me open it in a spreadsheet. It's easier. So I just generated this data just for this exercise. So what you have here is, think of this as sales data. The columns are business date. You have a sale ID. which store sold that, and the product sold. So this column, product sold column, comprises of a structure like this. You have a product ID colon amount separated by a pipe, and then product ID and amount, etc. So that's a structure like that. So that's the data. So what we want to do is we want to do a group by store and get the totals of sales for each product, group by store. So we want to get at a structure like this for each store. Make a structure like this, where for each product you'll get the total amount of sales. So that's what we want to derive from this data. Okay. So I mean, I plan to do this in two different ways. Okay, I think we have 10 minutes. We should be leaving soon. So one way is using just plain RDD. So there is no SQL involved. I have the second component that does the same thing using Spark SQL. So let me just run this. I think the best thing is to put this code on GitHub and then share this with you. But let me run this. So I'm just importing a library for random and date time.
SQL here, yeah?
No, this is not SQL, but this is just plain RDD, like operations on RDD. I read this whole data file into an RDD, and then do parse each line, get the values into a key value structure, and then group by. That's the operation I do. I'll put the code. It's easy if you follow the code. It's going to.
We call it RD code.
Sorry.
What's the code? In which language?
Oh, this is Python.
Oh, Python. Oh,
yeah.
Okay. But here in like this, if you write Hive or big, it's very simple.
Well, Hive supports SQL.
Yeah.
Yeah, you could do that. Yes. No, this is just to demonstrate how you bring up a cluster and do something in Spark, right? Yeah. And eventually, you could use the same cluster to run your machine learning algorithms from Spark MLlib, and you could use GraphX for graph algorithms and things like that. So I mean, I don't think we have time to go through all this code. So basically, what it's doing is it's bringing all the RDDs of the same key together, and for each of those structures, product sales from one to the other, it will somehow merge them and just sum it.
So does the RND take each row separately?
Yeah, it will process each source. All these can be worked on separately. That is the transformation. And then after that, group by is an action. It brings it up and then sums those structures together. Okay. So actually, those are just function definitions that does the kind of merging. And I have this file already on Google Storage. So that's the first line that's making the RDD. I'm just saying, go to Google Storage, read this file. And I'm also saying filter by. I don't want that first row to be read. So I'll just say don't read the first line because it has a header line, right?
So Google Storage is outside of Dataproc.
Outside of Dataproc, yeah.
Any credentials to access that file or is it Dataproc?
Well, if you create your folder, when you create a project on Google Storage, on Google Cloud, you are given a bucket. So if you put your files in that bucket, your folders in the bucket, you have access to it. You could share your folders as well with other projects, other users.
And all you're doing there with that line then is loading up the RDD in memory.
That's right, yeah. It loaded the RDD, and now I'm doing a transformation. PNLs, RDD.map, make product amount pairs. So it's making key value pairs within each RDD for product and amounts. So you have a line which is a sale ID, etc. store, and then product amount. It's a nested structure within that. And one more line I get. So right now it's lazy evaluation. It did nothing it just stored the information. And now the next action is I'll say save this output to a file. That is when everything else gets triggered, right? Oh, well, that's the Murphy's law, right? So, okay, I know what it is. Let me go to Google Storage. I think I have an output file there, which I should delete. Okay. So I should have deleted this, otherwise, so it's breaking down that into stages, and stages has, as I said, it's intermediate actions. And now if I go back to storage, I should see the file again. So, okay, we have another 5 minutes. I think we should wrap up. So it created this folder, and usually you'll see the output like this. Parts. If you have many parts, I made this into one partition, so you have one partition that is output. And anyway, let me save this file here. So that's the output. There are 9 stores, and for each product you have the total amounts, and so there are 9 records there. So that's how that works. And we could do the same thing with what's known as Spark SQL, which actually gives you a SQL kind of interface to that. I'll quickly show you the code. I don't think we have time to run that. So the code again looks like this. Let me give you. It's only this much, right? Only 3 or 4 lines. So in the first line, I'm reading the file. In the second line, I'm actually creating a data frame out of that with just, well, I could have skipped store sale ID here, store and then product sold, that structure. And I'm just manipulating the structure, and then I'm using something called explode. You know, it takes the structure it explodes that and makes one row for each element there. So these are some of the API elements that you need to get familiar with. Spark SQL functions like explode and things like that. You have something called split, and where if you have value, if you want to split it into 2 columns, you could do that. So we'll stop here.
So in this example or demo,
Yeah.
technologies that you use there. So you have used Yarn.
I've used Yarn, and the Spark program runs on Yarn.
Using Yarn, using Spark.
Yeah.
Using Spark.
Okay. Just a second. 1 second. Let me.